class and GS class in the BIS school. Today we're going to solve the first question in the Excel sheet. We know that the quantified energy levels of the hydrogen atom are given by the formula En equal to minus 13.6 divided by n squared electron volt as stated in the lecture. In the first question, he wants us to explain briefly the significance of the expression quantized energy and say why the hydrogen spectrum is composed of lines. So, the energy is quantized because the value corresponding to the different energy levels are discrete. We mean by discrete that they have a specific value. This produces spectrum of specific wavelength and frequency composed of discontinuous lines of specific value. Then, the second question, he wants us to calculate the values of the energies corresponding to the levels n equal 1, 2, 3, 4, and n equal to infinity. A reminder, we are given by the formula En equal to minus 13.6 divided by n squared electron volt. So we replace n by its value. We get the following values as stated in the lecture, and we have this figure always. Now in part B, we are given that the hydrogen atom is found in the fundamental state. Fundamental state is when n equal to 1. Calculate the minimum energy of a photon that is able to excite this atom, then to ionize this atom. To excite this atom minimum energy, let's take it from n equal to 1 to n equal to 2. Excitation equal to E2 minus E1. We found the values before, equal to minus 3.4 minus into minus 13.6 equal 10.2 electron volt. Ionized equal to E infinity, i.e. ionization minus E1 equal to 13.6 electron volt. Now in B2, the hydrogen atom receives separately 3 photons of respective energies, 11 electron volt, 12.75 electron volt, and 16 electron volt. Specify in each case the state of the atom and justify our answer. For E equal 11 electron volt, we have E equal E final minus E1. Implies that E final is equal to E plus E1 equal to 11 minus 13.6 equal minus 2.6 electron volt. Referring to the second question, no one of these is equal to minus 2.6 electron volt, then we have to neglect this energy. In part B, we are given that E is equal to 12.75 electron volt. We have that E equal E final minus E1 implies E final is equal to E plus E1 equal 12.75 minus 13.6 equal minus 0.85 electron volt, which is equal to E4 founded before. Another way of solving it is, if we didn't find them before, is stating that En is equal minus 0.85 electron volt, and using the formula we get that n equal to 4. In the third part, 16 electron volt, which is greater than the ionization energy, and we stated before if E photon greater than ionization energy, it goes to the ionized level and it commits us kinetic energy. Now that the hydrogen atom is being always in the fundamental state, receives now a photon of energy E. An electron of velocity v equals 7 times 10^5 meter per second is thus emitted. From the word emitted, we should know that we are in the ionized state, and now calculate E. Kinetic energy is equal to half mv squared. We get the answer in joule, we change it into electron volt. E is equal to E ionization plus kinetic energy in electron volt, we found it, equal to 13.6 plus 1.4 equal 15 electron volt. This excitation of the hydrogen atom. The hydrogen atom is found in the energy level n equal to 3. Specify all the possible transitions of the atom when it is in this excited. Thus, the possible transitions are from n equal 3 to n equal 1, n equal 3 to n equal 2, then from n equal 2 to n equal 1, as shown in the figure. One of these emitted radiations is visible. Calculate its wavelength. Referring to Balmer series stated in the lecture, it should be from n greater than or equal to 3 to n equal 2. So only one of them. To calculate the wavelength, E is equal E high minus E low, E3 minus E2 equal hc over lambda. We get the lambda, but don't forget to change the energy from E volt to joules. Thank you.